Okay, so in today's class, we will be going through the physical design of IoT. This is the second part of the main unit of introduction to IoT. Uh, so, uh, so when we take the course schedule under Unit 1, we have the introduction to IoT, and we are currently in the second title of the unit. So we have the physical design of IoT. After this session, we will have the logical design of IoT, IoT enabling technologies, IoT levels and deployment, domain-specific IoTs, and so on. So let's start with the physical design of IoT. So the physical design of IoT refers mainly to the hardware and network protocols that are used in IoT networks to collect information from sensors and establish communication with the internet and with other devices. Basically, the physical design of IoT means the hardware and the network protocols. And the physical design of IoT, therefore, can be divided into two main categories, and they are things and protocols. So under things, what we mean are like physical devices such as sensors, processors, communication modules, and so on. And in protocols, we are considering the protocols in link, network, transport, and application layers, which are used for the communication in the IoT networks. So in things, in the IoT, we mean the physical devices or the logical entities that we use to collect information and process the information. So the physical devices can be composed of sensors and processing boards, right? So that processing hardware refers to the microcontrollers. So we can consider the total system, which consists of the sensors and the microcontrollers as a thing, right? So the such kind of entity can range from a simple sensor to a complex machine or a system. So basically, in an IoT network, the edge device, the device at the edge of the network is known as a thing, right? So the device which is at the edge of the IoT network will be sometimes a complex machine like a robot or other industrial machine like some kind of a automated machine. And those machines or robots, let's say, have sensors in them which enable them to obtain sensor measurements, and they have processors in them which enable them to execute actions locally if needed, or they can send the data to a remote location where there's a computer that can do the computation. So when we talk about the IoT things, they will have the properties like those IoT things will have a unique identity, and they will be able to perform remote sensing, actuating, and monitoring. So what I mean is that they are able to do some sensing at the device level and take measurements of the environment. They can perform some actions at the edge, right? So at the device level, they can perform some functions like, for example, actuating means like turning on a motor, turning on a valve, and so on. And they can monitor their environment. Thirdly, they can exchange data with other devices, right? If they since they have communication modules and they have short range communication ability, if the neighboring devices also have the communication ability, they can directly communicate with the other devices, for example, using Bluetooth. Otherwise, they can communicate through the local server and gain access or communication to the other device and the other device in the IoT network. And they can also process either locally or remotely, right? So at the edge device level, they can do computations if they have enough hardware and software capability, or else they can send the data to the local server and do the computation there, or else they can forward all that data to the cloud and do the computation at the cloud. So in here, the unique identity must be given to the IoT thing. So that unique identity is given by different addressing forms. So we have IP addresses that will uniquely identify the devices. So basically, the IoT things are used for collecting and transmitting data to the cloud or the central processing systems. In IoT networks, as I said before, the edge devices will collect sensor measurements, and they will use different types of sensors for collecting the measurements. So depending on the application that is considered, different types of sensors will be used. So if we take into consideration some sensors that are used for like mini tasks, we can take LDR, for example, which is a light dependent resistor. So this resistor component can reduce or increase its resistance based on the light that it detects in the environment. So based on that condition, we can, design a circuit that can maybe switch on or off a light based on the intensity of the light in the environment. And secondly, we have the passive infrared sensor. So this sensor can detect IR radiation in the environment. So it can detect whether there's a human inside a room or not, right? So it can detect the heat in the environment. So it is used for applications like alarming systems and thief recognition systems and so on. And then we have smoke sensors. So these smoke sensors are used for situations where we want to detect smoke. So if we have different, if we have, for example, fire condition in our area environment, we need a smoke sensor to detect smoke in the environment. So it can measure the quality of the air in the environment. And then we have temperature sensor, which can detect the temperature in the environment and take measurements regarding that. And then we have the ultrasonic sensors. So these ultrasonic sensors are working with the ultrasonic waves, right? So we have these sensors which send a signal which is above the frequency of which is operating in a frequency above the frequency of our hearing range, so above 20 kilohertz, and then that signal will go and hit on objects, and then it will reflect back its signal. So depending on the delay that the signal is taking to return back to the ultrasonic sensor, the ultrasonic sensor is predicting the distance to the object, right? So it is therefore this sensor is used for close by object detection, right? So this is using the time of arrival concept, and it is useful for for example, building robots which can go through environments by observing objects in its environment, right? So when it want to autonomously go through a certain path, it needs to identify the objects that are around its environment, and for that activity, the robots can use ultrasonic sensors and define the kind of interferences that are there in the path. And then we have harder microcontrollers, right, that we can use in IoT systems, right? So these hardware boards that are used for processing at the edge of the IoT network, right? So we can take some sensor measurements, we can do the processing, and then we can send it over the communication medium over to the local server, right? So these hardware boards are coming with components that have dedicated sections allocated for power supply, communication, processing, storage, input, output, processors, and so on, right? So these microcontrollers are able to take input and give an output. They have a certain amount of storage capability. They have some certain amount of processing ability. They have communication modules, and also they can store some power in that module to do the necessary computations. So some examples of such kind of hardware boards are Arduino Uno, Node MCU, Raspberry Pi, ESP32, and so on. So there are other types of boards also in the world and in Sri Lanka as well. So these boards can be used for different applications. So depending on the application that we want to do in our IoT network, we need to select the suitable microcontroller. So when we take into consideration the microcontroller Arduino Uno board, the language used is based on C++. So this microcontroller is based on Atmega 32.8p, and it's having a clock speed of 16 megahertz. So this processor is very popular in the world because it is easy to use, and the coding is easy, and there are so many sample codes available in the internet for us to replicate some project that we replicate and modify any application that we want to implement. And it supports analog and digital inputs, and therefore this Arduino board has been very popular with beginner level like for beginner level projects, and then for small activities, small applications, small scale applications. However, there is a little bit of a disadvantage when we take into consideration the memory space, for example. So the flash memory is there is about 32 kilobytes, and RAM is about 2 kilobytes. So because of that, the amount of memory is not enough for large scale activities, right? Arduino Uno board is a really good board for working, but the amount of storage and the amount of processing that is available in the board is sometimes could be insufficient for some certain applications. Also, this Arduino Uno board is having only a single core. That means it is only having one processing unit, and therefore it is not able to do very high computational tasks. So in comparison, when we take into consideration the Node MCU, so this microcontroller is having much more kind of flexibility than Arduino board when it comes to when it comes to the the processing ability. So it has a dual core. So it has 2 cores with which it can do multitasking, and it can save time and also simultaneous processing. So this is possible with the Node MCU. And apart from that, it is also low cost in the market. And there are open source libraries from which we can take documentation information to develop applications and like algorithms in this controller. And also we are using a programming language known as Lua to code in this Node MCU. Also, there's a Wi-Fi module in this microcontroller, which enables us to connect this to the internet. Next, we are going to talk about the ESP32 microcontroller. So this has also a dual processor. It also supports Wi-Fi, and it has many input-output ports. Also, it supports Bluetooth and Bluetooth low energy communications, right? Apart from that, ESP32 also has touch sensing pins, and it has a built-in Hall effect sensors and temperature sensors. The Hall effect sensor is used for measuring any changes in the magnetic field in the environment, and the temperature sensor, of course, can measure the temperature. Apart from that, ESP32 can work both in active and sleep modes. So once we have these active and sleep modes, we can control the energy consumption of the microcontroller. So we can build our algorithms such that we can define at what moments it needs to stay active and in what moments it needs to sleep. So depending on our application, we can introduce the active and sleep modes to enable the microcontroller to only work when the data needs to be measured and processed and so on. So in all the other times, the microcontroller will be in the sleep mode, and that kind of algorithms will enable the microcontroller and the edge device to save more energy. And then when we talk about the Raspberry Pi, we have a more complex and more service-enabled microcontroller in Raspberry Pi. So in here, we have multiple USB ports. We have 1 gigabits of RAM, and we have 1.2 megahertz of clock speed. So we can do a lot of storage. We can do processing of data, and we have multiple types of input-output ports. We have HDMI connections, we have USB connection, Ethernet connection. Also, we have Wi-Fi modules on board and Bluetooth. Therefore, it can support many services, and also it supports Linux and Python, which allows it to develop multiple applications. So Raspberry Pi is good for applications where you need complex computations, and it is mostly, it is used in applications such as image processing, right? So which requires a lot of computation. So Raspberry Pi is a complex device. However, it provides a lot of services. Right. So next we are going to be talking about the second part of the physical design of the IoT. Right. So I said before that we have 2 parts. The first part is the things in IoT. So in things in IoT, we talk about the hardware at the edge of the IoT network, right? So at the edge of the IoT network, we have the microcontroller boards and the sensors. right? So those things comprise the things in IoT. So when we take into consideration the next part, which is the IoT protocols, the IoT protocols define how the communication between the things and the local server, and also next the cloud, and so on, happens in an IoT network, right? So IoT protocols define how the data is physically sent over the physical layer in an IoT network. So once we take the IoT protocols in the IoT protocol stack, we can divide them basically into four categories, depending on the corresponding to each layer, which are application layer, transport layer, network layer, physical and link layer. So starting from the bottom, we can start with the physical and link layer protocols. So we have the Bluetooth, Wi-Fi, near-field communication protocols, and so on. Then we have in the network layer, we have IP addressing, and so on. So we have the ability to give a unique address to devices in the network layer. And then the transport layer basically uses the UDP and TCP protocols. And then we have the application layer protocols. So we have MQTT, COAP, HTTP protocols. And there's ZigBee protocol, which goes through multiple layers. So likewise, there are these are examples of IoT protocols that are commonly used in IoT networks. So when we take into consideration the physical and link layer protocols, the physical and link layer is basically responsible for providing reliable data transfer across physical network links, right? So these protocols are enabling us to provide reliable data transfer between devices over a physical network link. So there are certain protocols that are examples for this. So they are Bluetooth, Wi-Fi, Ethernet, cellular, and so on. Oh, so we can take Bluetooth protocol and specifically Bluetooth low energy protocol. So this is a protocol which is low power, a short range wireless protocol that is used commonly in consumer devices such as wearable sensors and smartphone devices. So we have Bluetooth and Bluetooth low energy. They are two things. So Bluetooth low energy is a like a version of Bluetooth which uses a lower power than Bluetooth, and also it is used in multiple, wearable devices and short range communications. Right. So once you are using the Bluetooth technology, the Bluetooth communication is following a certain protocol once it is getting transmitted from a certain device. For example, from a wearable device to another receiving device. So the standards are defined in this Bluetooth low energy protocol. And so based on the standards, all the industries are following the specific same standard when they are building systems that are enabled with Bluetooth low energy. So these protocols are hence useful to make sure that different vendors do not implement different things. So in order for us to make sure that all the industries and academia are implementing the same devices or following the same standards when innovating a device, we define these kind of protocols. Right. So the next thing is the Wi-Fi protocol. So it is basically defined by IEEE 802.11. So this is the code for the Wi-Fi protocol. So it is a protocol that is widely popular all over in the communication field, and it defines the communication standards for the link layer. And there are different um, ways or different standards under the 802.11 protocol. So 802.11a protocol is a sub protocol of the main Wi-Fi protocol, and it will operate in a certain frequency, which is 5 gigahertz band. And next, when we take 802.11b, it will operate B, and 802.11g, they will operate in 2.4 gigahertz. So 802.11n will operate in 2.405 gigahertz. So likewise, different Wi-Fi protocols are defined for different frequencies. So if we are using a certain frequency, that depending on the frequency that we use, the protocol that is followed is different. And then we have the mobile communication protocol under 2G, 4G, 3G, 4G. So these mobile communication standards are defined for communications from the the telecommunication towers to our mobile devices. So they can have rates of about 9.6 kilo bits per second in 2G, and about 100 megabits per second in 4G. So for communication from the base stations to our devices, from the core network to our devices, we define the IoT protocol, which are corresponding to the 2G, 3G, 4G communications. So these protocols define how we connect to the telecommunication network and how the data packets will be sent, what are the messages that will be sent initially, and what are the feedback we will receive, at what time we need to send the data, at what time we need to send the control data, and so on. So these protocols will be followed by every industry person who's implementing these communication systems. Next, we have another short-range communication protocol known as LoRa WAN, so LoRa long-range wide area network. So this long-range wide area network, which is based on the LoRa technology, is a low-power, long-range wireless protocol commonly used in IoT applications. So once we want long-range communications for up to 8 kilometers, 10 kilometers, and with low power, we can use this LoRaWAN protocol. So we have this protocol in IoT systems, and based on our application, we can apply this LoRaWAN protocol for our devices. So once we need a higher long-range communications, we need to use this protocol. Next, when we take into consideration of the Ethernet connection, it follows IEEE 802.3 protocol, which is defining the standards for communication using the Ethernet links. So if the Ethernet link is a coaxial cable, it needs to follow 802.3. And if it is a copper twisted pair connection, it should use 802.3i. If it is a fiber optic connection, it should use 802.3j. If it is a fiber connection over Ethernet connection over fiber links, it should use 802.3a. So based on the communication medium, the standard that will be followed in sending the data over the Ethernet will be different. So we can use either coaxial cable, the twisted pair connection, or fiber optic connection, or fiber enabled Ethernet connection to connect our devices to the internet, right? So based on the different medium that we use, the standard that they will be following to enable the communication will be different. And next, we will be talking about the network layer protocols. So the network layer protocols will define the standard rules for receiving and delivering packets, data packets over the network. Right, so it will define the unique addresses to devices in the IoT network, and also it will define the format of the data packet in which we are sending the data. And when we talk about the network layer protocols, we have mainly IPv4 protocol, IPv6 protocol, 6LoWPAN protocols, and so on. So when we take into consideration the internet protocols, the IP protocols, they provide underlying standards to connect our devices to the internet. And also, once our devices are connected to the internet, a unique IP address is assigned to the device, right? So the internet protocols are basically assigning a unique IP address to the devices in the, for example, in the IoT network, right? So once we connect to the internet, the IP address will be allocated to us either by the router that we are accessing, or else if there's a DHCP server, that DHCP server will allocate the IP address to our devices, right? So the internet protocols will perform the addressing of the devices, and it will support in the routing of the packets from the source to the destination. And then the packet contains information of the source and the destination address. Right, so based on the data that is given in the packet, it is easier for the TCP and UDP protocols to find the destination and the source, destination device. And then, so the packet routing refers to the process of directing the data packets from the source to the destination across the network. Right, the IP addresses can be assigned by different entities depending on the type of the network. Right, so if it is a small scale network, like a small home or office network, the router will typically assign the IP address. Right, so this is the assigning of the IP address will be done by the DHCP, or Dynamic Host Configuration Protocol, which will automatically assign IP addresses to the devices as they connect to the network. In larger networks, such as corporate or business networks, the IP addresses will be assigned by a dedicated server known as the DHCP server. So in IoT networks also, IP addresses are assigned by a DHCP server. So basically there are two types of protocols, IPv4 and IPv6. Right, so IPv4 protocol is a 32-bit decimal address, and then IPv4 protocol will assign 32-bit decimal address to the devices. IPv6 will allocate 128-bit hexadecimal address to the devices. Right, so IPv4 address is the difference. The main difference between these IPv4 and IPv6 addresses is mainly due to the length of the addresses. So the IPv4 is a 32-bit address, while IPv6 is a 128-bit address. So because of that, IPv4 is able to provide unique addresses to about 4 billion devices. And in contrast, IPv6 is able to provide 340 under zillion addresses, about 1 into 10 to the power 36 devices. So it is a huge amount of devices, and therefore IPv6 addresses are estimated to be enough for addressing all the devices in the world. So when first initiating the IPv4 address scheme, the engineers thought that IPv4 address amount will be sufficient to address all the devices in the world. However, the 4 billion addressing was not enough for naming all the devices in the world. However, therefore, IP version 6 was introduced, which can provide higher number of IP addresses. So the main difference, as you can see in the IPv4 address format and in the IPv6 address format, is that in IPv4 format, we have 4 numbers separated by dots, and these numbers are all decimal numbers. In IPv6 address format, we have both characters and numbers, decimal numbers in the address, first thing. And the second thing is that they are separated by colons, right? So once we see an address, we can detect whether it is an IPv4 or an IPv6 address, right? So IPv4 address we represent as a 32-bit address, where we separate the 4 numbers by dots, and each separate number is known as octet. And this octet can take a value between 0 to 255, and the computer only understands numbers in binary format, and therefore we need to convert this IP address into binary format. Only then we know, like, the format in which the computer understands this IP address, right? So the IP address in its decimal format, if it is 66.94.234.13, we can denote its binary format by converting it into the binary numbers, by considering that there are 8 bits in each octet. And then we can convert the entire IP address into the binary format, right? So there are 4 octets in the IPv4 address. So there's one address that we can't use in any computer in the world, and that is the 127.0.0.1 address, which is the loopback address, right? So this loopback address is the address which tells the computer to check its connections, right, and its own network setup, right? So this address is used to check the connection to the internet, and therefore it is reserved for that purpose, and therefore no device is allocated this address. Further, when we convert into the binary format, we can see that this address is starting with a 0, right? That means this address is a class A address, right? So we have different classes that are defined for IPv4 addresses, right? So we have class A, B, C, D, E address classes, right? So however, these IPv4 version addresses are the only addresses that have these class types, right? IPv6 does not have the address class types. A general IP address is made up of 2 parts, right? So it is made up of the network address and the host address, right? So based on the allocated network address range and the host address range, these classes are defined as a standard, right? So the class A is defined for a large scale network, right? So it is defined to address or give addresses to large networks with lot of host devices. So if we have an IP address which starts with a 0, it is known as a class A address, right? So in there, um, uh, the first bit of the first octet will be 0. The bits in the remaining 3 octets will be representing the host address, and then the first octet will have any number between 1 to 126, right? So once we calculate the total amounts that the class A can serve, we can take 2 to the power 24 minus 2 devices. So it is nearly 17 million, right? So in here, we take the total number of possible IP addresses minus 2, right? So in here, we take minus 2 because we want to reduce the 2 addresses which we allocate for network identification and for broadcasting. So 2 addresses will always be removed from the host address range to find the total number of host devices that we can address using the specific class. So therefore, we have about 17 million, nearly 17 million host unique addresses that we can supply using the class A IP addresses. And when we take into consideration of the class B IP address class, we can use this class B to address a medium scale network. So in class B, we have the IP address starting from 10, and the rest of it will consist of the network ID and the host ID. So it will have a number between 128 until 191 in the first octet. So we can identify the class B addresses easily from these integers. So if it is a value between 128 up to 191, we can say it is a class B address. And then we have, once we compute the total host devices which we can uniquely identify, we can compute it as 2 into 16 because we have 2 bytes allocated for host addresses. So we can compute the total IP addresses as 2 into 16 bits minus 2, right? Because we have to allocate 2 addresses for other purposes. So we have nearly 65,534 devices that we can name using class B address type. Then we have class C. So in there we have the IP address starting from 110. And then the first integer of the class C IP address will be between 192 up to 223. And it is used for smaller network because once we compute the number of host devices that it can cater, it can only serve up to about 254 devices, right? And then when we take the class D, in class D, the first octet will have a number between 224 up to 239. And then it is used for multicasting purposes. So the devices who want to send communication from one device to multiple devices must have a class D address, right? So these class D address range is dedicated for multitasking purposes, multicasting purposes, right? So multicasting means one device is communicating with multiple other devices, right? So therefore, these devices must be having the class D addresses specifically to transmit and receive the multicasted information, right? And therefore class D is separately used for that. And then class E is separately used for military applications and research applications, right? And its first octet will be between 240 until 255. And then once we talk about the IPv6 addresses, we have in IPv6 address type, we have 128-bit hexadecimal address, which contain both characters and numbers, right? So there are 8 quartets we call each 4 number, which is separated by the colon as a quartet. There are 8 quartets, and so each quartet can contain either decimal number or a character, right? So we can define each of the numbers in the quartet. There are 4 numbers in the quartet. We can define each of the number in the quartet by 4-digit binary values, right? So likewise, we can expand each of the number in the quartet, and we can find the binary representation of each of the quartet. And by doing that for the entire hexadecimal number, we can find the 128-bit hexadecimal binary notation, right? So then I would like to talk about IPv6 over low power wireless personal area networks protocol. So this protocol is known as 6LoWPAN network. So this protocol is used for low power, low bandwidth wireless ad hoc networks, right? So in wireless sensor networks, this protocol is used, which consumes less power and less bandwidth, right? So the reason for such kind of less power and less bandwidth is because this protocol enables the system to compress the IP header such that the packet size is made smaller. So once the packet size is made smaller, the transmission of the data packets is done with less power and energy, and therefore it requires less energy. And apart from that, the maximum size in the standard IPv6 data packet is normally 1024 bytes. However, in 6LoWPAN protocol, this data packet size will be reduced to up to 127 bytes. So because of the header compression, the size of the data packet was reduced significantly from 1024 up to 127. And therefore, it is widely used in wireless sensor networks and in ad hoc networks where we don't have enough energy at the device level and we need more energy efficient communication protocols. So this 6LoWPAN protocol is used for such kind of less energy networks and applications related to that. Right, so then we have transport layer protocols. So the transport layer protocols are basically TCP and UDP. The TCP protocol is the connection-oriented protocol, which means that it establishes the path in which the data packet will be delivered from the source to the destination before sending the data between the devices, right? So therefore, TCP is a connection-oriented protocol, right? It provides a reliable, ordered, and error-checked delivery of data between devices over the IP network, right? In contrast, UDP, or the User Data Program Protocol, is a connectionless protocol, right? So it is a packet switched protocol where we send the packets in a random manner in all directions, and once we receive feedback from the intermediate nodes and from the destination node, we send the data in a particular direction or in a particular algorithm such that the data are reliably received at the receiver end. So this protocol is used in time-sensitive applications and in very small data exchanges. So this is a transaction-oriented protocol, However, this does not guarantee reliable delivery. However, this is very popularly used protocol, and it is a connectionless protocol. So it does not need to create a like a path or the route between the source to the destination before sending data. Rather than that, it uses a very random method of sending data packets from the source to the destination without the knowledge of the exact path through which it is sending its data to the destination. So I will end by that section. So from the next class onwards, we will talk about the application layer protocol specific for the IoT networks. So I would like to also mention that the recommended reference book for this course is Internet of Things, a hands-on approach. So I would like to recommend this book for you as a reference book for this module. So by that, I would like to end the lecture for today. So if you have any questions, you can put in the chat. I will answer the questions, or else you can leave the meeting.